Here's another dimensional analysis question which looks at friction in pipes, but again from a dimensionless point of view. So in this case, we have to somehow quantify the pressure drop due to friction in a long smooth pipe, and we have to use a few things such as the average flow velocity, the density, the viscosity, and pipe length and diameter. Okay, so we've got this relationship here, which pretty much states that. So we've got our variables, and then we have to see how we can combine them to get this non-dimensional form. Now, this might be something that, as a first-year engineering student, you might see in your homework, in your exam, in your tests, and if you'd like to see anything similar to this on the channel, let me know in the comments. So I'm going to proceed doing this in the usual way, which is using the Buckingham Pi theorem. But then I will start by first drawing out or writing out all the variables. So first of all, we have this change in pressure. Then we have the velocity v, we have the density, we've got viscosity, length, and diameter. Okay, so the first step is counting how many we've got, and you can see that we have 6 variables. One more thing to note is that I will just ignore part B of the question. Part B is just plotting. Yeah, so we'll just do part A where we use the Buckingham Pi theorem to write the dimensionless form of this relationship. And then in the second step, we're going to write the units for each variable. So for the pressure, for the change in pressure, we know this is measured in, let's write it here. So it's newtons per meter squared, that's pascals. Now that is kilograms meters per second squared over meters squared, which is kilograms over meter second squared. So I'm not going to use kilogram meters seconds and so on. Instead, I'm going to use mass instead of kg, and instead of meters, I'm going to use length, and instead of second, I'm going to use time squared. So that's going to be ml to the minus 1 t to the minus 2, like this. Okay, and then for the third one, we have, actually, this is still the second step. So for the second variable, we have density, or let's do velocity instead. So velocity is length over time, or LT to the minus 1. Then we have density, and density is mass L to the minus 3, right? Kilograms per meter cubed, basically. And then we have 3 more. So we've got mu, I think was the next one, viscosity. So this normally is kilograms per meter second. So kilograms is mass, meter second is length, time, like this. Then length is length, okay? And then diameter is also length. Okay, right. So now we count how many independent units we've got, and we have 3 units. Right, we've got M, we've got L, and we've got T as well. So what we then do, well, we find the number of pi groups. So let's say this is step 3. So the number of pi groups is number of variables minus the number of units, just 3, and therefore we have 3 pi groups. So we have pi group 1, pi group 2, and pi group 3. So at this point, we just have to decide what we're going to include in each pi group as the main variable, and then the rest of them are going to be repeating variables. So let's say that for the first pi group, we're going to include pressure, or delta P, as the main variable, because that's the thing we're interested in a way, right? So that's going to be delta P. And then for the second pi group, we have, let's say we can use velocity. Technically, you can use any one you want, but yeah, I think using those in particular makes things make more sense in the end, as you'll see. And then for the last one, we have, let's say, length. Shall we say length or shall we say diameter? Let's say length, okay? and those are the main variables, and the rest of them are repeating. So the repeating variables are going to be density, viscosity, and we used length, so the last one has to be diameter. Okay, so we have rho, mu, and d. So let's put rho, mu, and d, and then rho, mu, and d, and finally rho, mu, and d, like this. Okay. So now we just have to find how those variables are related to each other such that the end result should be dimensionless. So let's start with pi1. So pi1 is going to be delta p, our main variable. And then we have rho to the x, mu to the y, and d to the z. And we say this has no units. And then we're going to write down the units of each variable. So for delta p, we know that's ml to the minus 1, t to the minus 2, because we got that from here. Okay, so ml to the minus 1, t to the minus 2. And then we have ml to the minus 3 to the power x. And then we have mu to the power, okay, let's actually write mu as ml to the minus 1, t to the minus 1. So ml to the minus 1, t to the minus 1 to the power y times diameter, which is a length, to the power z, and this should be m to the 0, l to the 0, t to the 0. So let's collect the m terms first. So we have m to the power of 1 plus x, and then plus y, and then we have l to the power of minus 1 minus 3x minus y, and then plus z. And finally we have time, which is t to the minus 2 minus y, and that's it. So that's m to the 0, l to the 0, t to the 0. So now we compare the powers. And we have for m, 1 plus x plus y is equal to 0. Then we have minus 1 minus 3x minus y plus z is equal to 0, right? So what I'm basically doing is I'm saying this is equal to this is equal to this, and this is equal to this. So 1 plus x plus y is equal to 0. This thing is also equal to 0. And finally, minus 2 minus y is equal to 0. So the last one is the easiest to do. So that gives us y is equal to minus 2. Then we can use that here to find what x is. So we have x is minus 1 minus y. So that's minus 1 plus 2, which is 1. So we found y and we found x. And we use that to find z. So z from the second equation is going to be equal to 1 plus 3x plus y, which is 1 plus 3, and then minus 2, which is 2. So we found x, we found y, and we found z. So now we can say that pi1, the first pi group, is going to be equal to delta p times density to the power x. So density to the power x is density to the power 1. And then we have times viscosity, should be viscosity to the power minus 2. And then we have diameter. So diameter is to the power z, or just to the power 2. So pi1 is, let's see, it's rho times delta p times d squared over viscosity squared. Okay, so that is the first pi group. Now let's do the same thing with the second pi group. So the second pi group was, let's see, this one here. So it's got velocity to the power 1. Then we've got rho to the power x, we've got mu to the power y, and then we've got diameter to the power z. And again, this should have no units. And now we write the units and do the same thing as before. So for velocity, we have L t to the minus 1, and then we have m L to the minus 3, everything to the power x. Then viscosity is m L to the minus 1, t to the minus 1 to the power y. And then diameter is just this. And as usual, this should be n to the 0, L to the 0, T to the 0. Okay? Keep in mind that the X, Y, Z in here are different from the X, Y, Z from here. I'm just using the same letters for convenience. So let's collect all the terms. So first of all, we have, let's start with n. So we have m to the power x plus y, and then we have times L to the power 1 minus 3x minus y plus z, and then we have t to the power minus 1 minus y equals to the same thing. So m, l, t, everything to the 0. What do we do now? We compare the powers as usual. So we have x plus y is equal to 0, which we write like this. Then we have the second thing. So 1 minus 3x minus y plus z is just double check. So it's minus 1 plus z. Okay, looks fine. Which should be the same thing as here. Yes, so this is equal to 0, and then we have minus 1 minus y is equal to 0 as well. Okay, so y is equal to minus 1 straight away. Then from here, we write that x is equal to 1. So we found x and y, and now we found z. So z is going to be equal to minus 1 plus 3x plus y. So we have minus 1 plus 3 minus 1. So it's 3 minus 2, which is 1. So we found x, we found y, and we found z. Okay, so we did that in a similar fashion to what happened here, essentially. Okay, so now we write the second pi group as follows. So this is going to be equal to v, the velocity, then we have density to the power x, which is to the power 1, then we have viscosity to the power y, which is minus 1, and then we have diameter, not length, diameter to the power 1. So this is rho times v times d over mu. And if you look at it, you'll realize that this is actually the Reynolds number, okay, for a pipe, because it's got diameter in here. So we're sorted with this. Now the third pi group, I'll just take a shortcut to do it. So let's first write it in the proper way, which is like this. So we have L rho to the x, mu to the y, and then diameter to the power z. Now, there's an easy way to see what should be done here, and you know for a fact that length is to the power 1. So the simple way to do it is to realize that to get a non-dimensional parameter here, you need something, because this is length on the numerator because it has power 1, so you need another length in the denominator. And there is a length in this combination of variables, and its diameter. So if z becomes minus 1 and x and y become both 0, then we're sorted, right? We have pi 3 equals L over D, and that's your third pi group. So the last thing to do is just to write the formal relationship between the parameters. So I'll just choose to write it as pi 1 is a function of pi 2 and pi 3, like this. So pi 1 was this. So I have rho delta p d squared, I think, over mu squared. So this is a function of the Reynolds number, that's the pi 2, it's rho vd over mu. Rho vd over mu, and finally we have, I think it's L over d. Yes, like this. Okay, so this is the non-dimensional relationship between the pressure loss across a pipe as well as other parameters which might influence that, such as density, viscosity, pipe diameter, pipe length, and so on. Okay, and that's the end of the question.